Swayam Prabha. Digital India. Educated India.
Welcome back to the video course on fluid mechanics. In the last lecture, we were discussing about the fully developed turbulent boundary layer and the drag calculations. We have calculated the coefficient of drag and various other parameters as we have seen here. So, we were discussing about the flow over a flat plate, and then we have seen that initially there is a laminar zone and then transition zone, and then we were discussing about the turbulent zone. So, for the turbulent zones, we have seen that starting from the Blasius 1/7 power law, we have shown the shear stress equations, and also we have shown that this boundary layer thickness delta by x is equal to 0.379 divided by rx to the power 1 by 5 as in this equation, and then we have seen the local friction coefficient Cf is equal to 0.059 divided by rx to the power 1 by 5, and then from the calculations for the Reynolds number greater than 10 to the power 7, Prandtl calculated the coefficient of drag Cf as 0.455 divided by log 10 RL to the power 2.58, and then using this various coefficients, various equations which we have seen, we can calculate various parameters like the drag force, the local drag force at various sections, and the corresponding drag coefficient, and also we can calculate the total drag on a flat plate, and then we can also calculate the drag coefficient for the given plate. So, before proceeding further, we will briefly discuss a small example here. So, here the example problem is a 20 km/h wind blows over a 6 meter flat plate if the density and kinematic viscosity of air are 1.2 kilogram per meter cube and 1.5 into 10 to the power minus 5 meter square per second respectively. Calculate the force per meter width of the plate and also estimate thickness of the boundary layer at the trailing edge. So, here the problem is that say we have a flat plate of size say 6 meter size, and then a 20 km/h wind is coming, and then say the density of the air rho is 1.2 kilogram per meter cube and kinematic viscosity is 1.5 into 10 to the power minus 5 meter square second. So, for this case we have to find out the force per meter width on the plate. That means say this is the plate, so then per meter width we have to calculate the force per meter width, and also we have to estimate the boundary layer at the trailing edge. So, this is the leading edge and here is the trailing edge. So, here we have to say find out the boundary layer thickness. So, to solve this problem, first say the wind velocity is given as 20 km/h. So, we will convert the wind velocity into meter per second. So, 20 into 1000 divided by 3600 will give 5.56 meter per second, and then initially we will find out the Reynolds number. So, once we find the Reynolds number, we can identify whether the flow regime is in laminar or transition or turbulence, so that we can use the appropriate equation. So, here if you find the Reynolds number R is equal to UL by nu. So, here U is already obtained as 5.56. So, 5.56 into 6 divided by the kinematic viscosity 1.5 into 10 to the power minus 5. So, that will give the Reynolds number as 2.22 into 10 to the power 6. So, here we can observe that the Reynolds number obtained is more than the critical Reynolds number 5 into 10 to the power 5. So, the boundary layer flow is in the turbulent flow regime. So, we can utilize the equations which we have seen in the last lecture for the coefficient of friction drag and also various other parameters. So, the coefficient of friction drag for the turbulent flow, when the boundary layer is in the turbulent flow regime, so we get CDF is equal to 0.074 divided by REL to the power 1 by 5. So, this if we calculate after putting this Reynolds number, in the previous slide we have seen that Reynolds number is equal to 2.22 into 10 to the power 6. So, if we put this, we will get CDF, the coefficient of friction drag, as 0.00398, and then the drag force on one side of the plate per unit meter width is given as, say, the coefficient of drag multiplied by area into rho u square by 2. So, here CDF we obtained as 0.00398 into 6 into 1. So, we consider 1 meter width of the plate. So, 6 into 1 into 1.2 into 5.562 square rho u square by 2. So, that is equal to 0.4429 Newton. So, thus we get the drag force on one side of the plate per meter width. And then the second part of the question is to find out the boundary layer thickness at the trailing edge, that means end of the plate, as we have already seen. So, here x is equal to 6 meters. So, we can utilize this equation which we have just seen in the last lecture for turbulent boundary layer flow. Delta is equal to 0.379x divided by Rex to the power 1 by 5. So, here that is equal to 0.379 into 6 divided by 2.22 into 10 to the power 6 to the power 1.5. So, we get the boundary layer thickness as 0.1217 meter. So, this is a simple example. So, here like this, say, now whatever we have seen so far is the boundary layer and its related the drag force, friction drag, pressure drag, all the different kinds of drag forces. So, the based upon what we have studied so far, we can say solve different kinds of problems where, say, to calculate the drag force or to find out the drag coefficient, and then also other parameters like shear stress, and then also like say the force at particular location. Like that we can use the various equations we have seen in the last lecture as far as turbulent boundary layer and corresponding drag is concerned. And now we have seen the drag coefficient, the drag force, and the boundary layer as far as laminar flow is concerned, and then also we have seen the turbulent flow is concerned, the boundary layer flow is turbulent. So, now we have already seen there can be a transition from laminar flow to turbulent flow. So, if say the boundary layer is, if you want to find out the various flow parameters or various, say, like a coefficient of drag of the drag force, wherever simultaneous existence of laminar and turbulent boundary layer or the transition range comes, then we can say we have to use either the laminar concept as well as turbulent concept, and then we have to find out the various parameters. So, next topic is simultaneous existence of laminar and turbulent boundary layers. So, here you can see that this is the, here also we consider a flat plate which we have seen in our earlier derivations. So, here also the flat plate is placed like this, and then the free stream velocity is coming this direction, and then this is the leading edge and here is the trailing edge. So, initially as we have seen, there is the laminar boundary layer is developed, and then we have the transition and then the turbulence. So, this is the where the transition, and that is where we want to see how to calculate various parameters. So, here the length of the plate is sufficiently large, so that we can say here the boundary layer starts as laminar, then we have the transition, and then we have the turbulent. So, this depends upon the length of the plate. So, if the length is very small, then we may get only laminar or turbulent, but then here, as here in this figure shows, we have starting from laminar, then we have a transition and the turbulent boundary layer. So, now for this kinds of problem, so the existence of laminar boundary layer over a small initial length decreases the total friction drag exerted by the fluid over the plate. So, as we can see, the say initially the length of the plate in such a way that there is a laminar boundary layer exists. So, this existence of the laminar boundary layer over a small initial length actually decreases the total friction drag exerted by the fluid over the plate. So, now if you consider the ratio of the coefficients of friction drag in laminar and turbulent boundary layer. So, we have already seen the coefficient of friction drag as far as laminar boundary layer is concerned. Also, we have seen the coefficient of friction drag for turbulent boundary layer is concerned. Now, if you consider the ratio of the coefficients of friction drag in laminar and turbulent boundary layer, we can write Cf laminar divided by Cf turbulent is equal to 1.328 square root of RL, where RL is the Reynolds number. So, this is corresponding to the coefficient of friction drag for laminar boundary layer, and then Cf, the coefficient of friction drag for turbulent boundary layer, we have already seen it is 0.074 divided by RL to the power 1 by 5, where RL is the Reynolds number. So, this is the ratio 1.328 divided by root L divided by 0.074 divided by RL to the power 1 by 5. So, this we can show that this is equal to 17.94 divided by RL to the power 3 by 10, where RL is the Reynolds number. So, now the transition stage with reference to the earlier figure which we have seen. So, the friction over an initial length x over which the boundary remains laminar is obtained as. So, here if you refer to this figure. So, now where this length, the transition from laminar starts as far as this length is concerned. So, the friction over an initial length x over which the boundary remains laminar is obtained as FDF laminar is equal to 1.328 Rx, the Reynolds number, critical Reynolds number to the power 1 by 2 into half rho u infinity square into x, where u infinity is the free stream velocity, Rx is the critical Reynolds number at that location, that means at x. So, here the Rx critical is the critical Reynolds number, which signifies the change of flow in the boundary layer from laminar to turbulent. So, whenever the Reynolds number changes at this critical locations, then the transition starts from laminar to turbulent. So, generally the experiments, various experiments conducted by researchers shows that this critical Reynolds number can be 5 into 10 to the power 5 as far as problems like this flat plate is concerned. The critical Reynolds number where this transition start is 5 into 10 to the power 5. So, now if we use this value 5 into 10 to the power 5, then we can show that the friction drag of turbulent boundary layer over the rear portion of the plate, that is from a distance x to L. So, here x to L means, here you can see that if this is the transition range and then this L is at this end. So, now with reference to this, now the friction drag of turbulent boundary layer over the rear portion of the plate, that is from distance x to L, is FDF turbulent, that is equal to, say if you consider this as turbulent, then 0.074 L divided by RL to the power 1 by 5. This is as far as turbulent boundary layer is concerned, minus 0.074 x Rx to the critical to the power 1 by 5 into half rho u infinity square, where u infinity is the free stream velocity and rho is the density of the fluid. So, x is this critical location. So, and then this expression gives the friction drag for the boundary layer, turbulent boundary layer, and then total friction drag, as we can see, we can add the FDF is equal to total friction drag is equal to FDF laminar plus FDF turbulent. So, now in this transition stage, say there is simultaneous, we can say that when this between this range, there is sometimes we can consider laminar as well as turbulent. So, the total friction drag, we can add this FDF laminar plus the drag force, friction drag for laminar plus frictional drag for turbulent. So, we have already seen earlier this frictional drag for laminar case is concerned. So, this the Reynolds number critical, Reynolds number with respect to Rx critical. So, this FDF laminar is equal to 1.328 into x divided by Rx to the power Rx critical to the power 1 by 2 plus then this term 0.074 L divided by RL to the power 1 by 5 minus 0.074 into x divided by Rx critical to the power 1 by 5 into half rho u infinity square. So, this gives the total frictional drag as far as the simultaneous existence. So, here as we have already seen the simultaneous existence of laminar and turbulent boundary layer. So, in this range, so we get the total frictional drag as FDF is equal to 1.328 x divided by Rx critical to the power 1 by 2 plus 0.074 L divided by RL to the power 1 by 5 minus 0.074 x divided by Rx critical to the power 1 by 5 into half rho u infinity square. So, where x is that critical distance where the Reynolds number is critical, say for the flat plate case as we have seen it is 5 into 10 to the power 5 and then RL is the Reynolds number at the trailing edge of the plate and L is the length of the plate. So, this gives the total friction drag for the concerned problem wherever the simultaneous existence of laminar boundary layer and the turbulent boundary layer case. Now, in the equation of total frictional drag, if we put the critical Reynolds number as we have seen Rx critical is equal to 5 into 10 to the power 5 and then if you consider this x is equal to, since if you consider say a linear variation with respect to this Reynolds number, that means we can write x by Rx critical is equal to L by RL. So, if you use that linear relationship and then put x is equal to L into Rx critical divided by RL, we get the total friction drag FDF is equal to 0.074 divided by RL to the power 1 by 5 minus 1700 divided by RL into half rho u infinity square into L. So, this is the after substituting this value of the critical Reynolds number Rx 5 into 10 to the power 5, we get the total frictional drag as this quantity. This is the expression, and now from this we can see that the friction drag is equal to, so this is per unit width which we consider L is the length. So, from this expression we can write the coefficient of skin friction is equal to Cf is equal to 0.074 divided by RL to the power 1 by 5 minus 1700 divided by RL. So, this gives the coefficient of skin friction wherever the case which we consider simultaneous existence of the laminar and turbulent boundary layer. So, like this we can now we found the skin friction coefficients and then total friction drag. So, similarly we can find out other quantities of shear stress and other parameters we can determine as far as the drag force and drag coefficient as far as this flat plate case is concerned. So, very similar way other problems also can be considered and we can derive various relationships for coefficient of drag, coefficient of frictional drag, the shear stress, like that various parameters. So, now let us consider the various cases, say depending upon the various parameters, how the drag coefficient change and then how the effect of parameters like Froude number or the Reynolds number or the shape of the object over which the flow takes place. So, now here we discuss the drag coefficient data and examples. So, net drag as we have seen, net drag is coming from the pressure drag and the shear stress effects. So, in most cases net drag we represent as CD. So, the drag coefficient of an object depends upon various parameters. So, this parameters say depends even what is the shape of the object or which the flow takes place, or which orientation we put, say even the same body, or like depends upon the fluid flow parameters. So, the first case, here we discuss the drag coefficient, how the changes as far as drag coefficient takes place with respect to drag coefficient takes place for various shapes of the bodies and various examples that we consider here. So, the various parameters which has got some effect as far as the drag coefficient is concerned. First one is the shape of the object. So, the shape of the object is concerned, we can have different shapes as far as body is concerned. We can have the blunt bodies like a sphere or a cylinder, or we can have the airfoil which is streamlined. So, the shape of the object can be streamlined to blunt body. So, accordingly we can show experimentally that the drag coefficient also varies. So, the drag coefficient, as we have seen, drag coefficient is based upon the frontal area or platform area. So, coefficient of drag is equal to the drag force divided by half rho u infinity square into A. So, where rho is the density of the fluid, Fd is the drag force, u infinity is the free stream velocity, and A is the area, plan area. Either depending upon the case, it can be frontal area or the platform area. So, now as I mentioned, say whether the same body which way we place. So, here say for example, if you consider this as a flat plate, then this flat plate, if you place it just like this, or if you place, say the free stream velocity is in this direction, then whether you place this plate in like this, or if you place this plate like this, or if you place the plate like this. So, depending upon this, the drag force or the drag coefficient changes. So, now here in this slide, a graph taken from Munson et al. Fluid mechanics textbook by Munson et al. The drag coefficient based upon the shape dependency of the drag coefficient is plotted here. So, here you can see the drag coefficient for an ellipse with the characteristics area, either frontal area, that means A is equal to B into D, where B is the length and then D is here. If you consider an ellipse, then this is L and here this is D and B is the length, or platform area will be A is equal to B into L. So, if we plot the coefficient of drag, so through experiments we can find out the coefficient of drag, or you can first find the total drag force, and then from which we can find the drag coefficient CD is equal to Fd divided by half rho u infinity square into A. So, from this now if you plot the coefficient of drag on y axis and say this typical case of ellipse, that means where L is this and D is this dimension. So, L by D on the x axis, then you can show that depending upon the shape. So, how by varying whether using B into L or B into D, like that, then you can show that the coefficient of drag is varying like this. So, now this case, if you use this, say corresponding to a flat plate normal to the flow, you can show that the drag force will be about 1.9. So, here it is shown here, the flat plate normal to the flow, the drag coefficient will be, drag coefficient CD will be about 1.9, and then say if the flat plate is put parallel to the flow, then you can see it is very small value, the coefficient of drag is very much reduced, then you can see it is almost say 0 or it is 0.001 or 002, like that a very small value is obtained. So, that is why I mentioned, when say even the body over which the flow takes place, how you place it, if it is whether it is normal to the flow then the drag force, as we have seen the case flat plate, the drag coefficient will be much higher. Or if you place the flat plate which we consider parallel to the flow, then the drag coefficient will be much lower as shown in this plot. So, similarly, so this figure shows as far as an ellipse is concerned of this shape. So, you can see that how the variation takes place starting of this like this, say given as CD is equal to FD by half rho u square B, corresponding to the whether which way we take, either we take a planform area or we take the frontal area corresponding to the ellipse, that is for this, and then this thick line is concerned CD is equal to FD by half rho u square into B into D. So, that is corresponding to this. So, here in this case the B area is B into 1 the considered. So, like this. So, this is corresponding to Reynolds number 10 to the power 5. So, like this we can show that depending upon the shape of the body, the drag coefficient changes. So, or effectively the total drag is also changing. So, due to these changes, say we can design say various say automobiles like bus or car, or say if you depending upon what shapes you give. So, the drag force will be can be reduced, and then the vehicle will be, we can make it much more efficient while driving. So, that is the importance of this studies on this drag force. So, similarly, if you consider say airfoil, so compared to a sphere or a blunt body, then you can see that the drag force is we can reduce too much, and then that is why this we can make it streamlined, and then we can reduce the drag force. So, that means the drag force or the coefficient of drags, say it the shape of the body has got considerable influence on the drag force or the coefficient of drag. So, that is the first component or first parameter which say affect the drag force or drag coefficient. And next one is the Reynolds number. So, here we discuss the drag coefficients and its dependence on the Reynolds number. So, we have seen that say depending upon the flow, that means depending upon the velocity, the flow can be either laminar or turbulent. So, in the last lecture as well as just now we have discussed the dependency on this Reynolds number. So, this Reynolds number is also another important parameter, so for drag coefficient. So, how the whether drag coefficient is increasing or decreasing depending upon the Reynolds number. So, as far as Reynolds number is concerned, there are three categories. One is very low Reynolds number flow, so that we can show that the inertia are negligibly small, and then second one is moderate Reynolds number flow where laminar boundary layer is taking place, and then third case is high Reynolds number flow where the boundary layer is turbulent. For very low Reynolds number, the coefficient of drag, we can show experimentally that the coefficient of drag varies inversely with respect to the Reynolds number, and then the coefficient of drag changes drastically when the boundary layer become turbulent. So, this we can show experimentally. So, the coefficient of drag is very much, or the drag force is very much dependent upon the Reynolds number of the fluid flow, and then say if the flow is laminar, then we can show that coefficient of drag varies inversely with respect to Reynolds number, and when the flow become turbulent, there is drastic change as far as coefficient of drag is concerned, and whenever the Reynolds number is very low, the inertia are negligibly small, and then also the drag force is very much changing, whether it is low Reynolds number or moderate Reynolds number or high Reynolds number flow. So, this here this slide shows the coefficient of drag for flow around a sphere at different Reynolds number. So, here you can see that say the coefficient of drag is plotted on the y axis and Reynolds number on the x axis. You can see that. So, here this is the case of flow over a sphere. So, here is the sphere and then the flow is in this direction. So, if we plot the coefficient of drag versus Reynolds number, then we can see that whenever the Reynolds number is much smaller, then the coefficient of drag is much higher like this, and then when the Reynolds number is increasing, say when the flow is becoming say laminar to this, you can see that it is coefficient of drag is keep on reducing say until this critical Reynolds number range is reached, and again it is going down like this, it is further reducing to the range of 10 to the power 6. So, this is the coefficient of drag versus the Reynolds number for flow around a sphere. So, then you can see that it is coming down to a level, and then further when the Reynolds number is increasing, that means the flow become totally turbulent, then the coefficient of drag is again slightly going on increasing like this. So, this we can experimentally show that depending upon the Reynolds number. So, for very low Reynolds number, the coefficient of drag is much larger, and then when the flow become say in the laminar range up to 10 to the power 5, it keeps on reducing, and then again there is again further reducing in the when the transition ranges, and when the flow become further turbulent, again the coefficient of drag is slightly increasing as shown in this slide. So, this shows the dependence of the coefficient of drag with respect to the Reynolds number of the fluid flow. So, here in this slide, so the drag coefficient for different Reynolds number values are plotted for various shapes. So, we have already seen depending upon the shape of the body, the drag force change, and now if we consider the Reynolds number, also the drag force change for the same body. Now, depending upon the shape as well as the Reynolds number, you can see that here in this slide, say for various shapes starting from vertical flat plate and the same flat plate placed in horizontal, then circle, then ellipse, airfoil, like that for various shapes. Here the coefficient of drag is plotted with respect to the Reynolds number. So, here you can see for vertical flat plates we have maximum coefficient of drag. So, if you since you can see that the vertical plate is placed like this, the vertically, so the flat plate is placed vertically. So, we have the maximum coefficient of drag, and then this is almost constant with respect to the Reynolds number, whether it is laminar or turbulent. The for vertical flat plate you can see that the coefficient of drag is maximum, and it is like this. And then if you take a cylinder or circular shape, then you can see that with respect to the Reynolds number, the drag force is say in the laminar range it is almost same, and then the flow become turbulent, then you can see that the when the further the Reynolds number increase, then for circular shape you can see that the coefficient of drag decreases to certain range, say here up to 10 to the power 6 something like that, and then it is slightly increasing as shown in this figure. And if you consider an ellipse shape, then you can see here the coefficient of drag in the say laminar range, it is initially slightly increases and then it keeps on decreases. You can see that in the transition stage it is keep on decreasing, and further for when the flow become turbulent, then you can see that again the coefficient of drag is increasing like this. This is the case for ellipse, and then the streamlined body like airfoil, you can see that when the Reynolds number increases, you can see that the coefficient of drag is decreasing, keep on decreasing like this, and only a small change whenever further increasing Reynolds number in this range for airfoil of this shape. And then flat plates placed parallel to the flow is concerned, you can see that this is with respect to the Reynolds number, laminar range it is decreasing sharply, and then whenever it is turbulent, then you can see that it is slightly going on increasing like this. So, this slide shows how the coefficient of drag or drag force changes with respect to the shape of the body and then with respect to the Reynolds number. Then Some other important parameters where the drag force will be changed or coefficient of drag changes include the compressibility effect. So, if the velocity of the object is sufficiently large, then compressibility effect become important and coefficient of drag becomes a function of the Mach number. So, you can see that here the Mach number is the important parameter, dimensionless number. Mach number is equal to the u by c, where u is the free stream velocity and c is the speed of the sound in the fluid. So, the coefficient of drag is usually independent of the experiments. Various experiments conducted shows that the coefficient of drag is independent of Mach number up to about 0.5, and then for most objects the coefficient of drag increases dramatically in the vicinity of, whenever the Mach number increases from 0.5, it is say up to 1, it is the coefficient of drag also increases. So, this is say the effect of the compressibility. So, the compressibility of the fluid has got effect on the drag coefficient or the drag force. So, especially say the flow which we consider, say if it is fluid like water, then the effect will be very negligible, but if you consider air flow, then you can see that the compressibility effect will be much higher, and then when the Mach number increases to 1, there is coefficient of drag is dramatically increased, but up to about 0.5 we can show experimentally that there is not much effect on the coefficient of drag with respect to the compressibility of the fluid. Then another important parameter as far as drag force and coefficient of drag is the surface roughness. So, we can see that say the same body, say if it is smooth, then the coefficient of drag or the drag force will be different, and if it is rough, the coefficient of drag will be different. So, depending on body shape, the increase in surface roughness may increase or decrease the drag. So, this depends upon the shape of the body also. So, if the boundary layer flow is turbulent, then experiment shows that the surface roughness may alter the Reynolds number and the shear stress changes and the net drag may increase. So, this we can show experimentally, and for streamlined bodies the drag increases with increasing surface roughness. So, the streamlined bodies like the airfoil, we can show that the drag increases with increase in surface roughness. So, to reduce the drag, we have to keep the surface of the body like airfoil, we have to keep it much smooth, so that the drag can be decreased. And for blunt bodies like circular cylinder or sphere, we can show that the increase in surface roughness increases. So, depending upon the increase in surface roughness may decrease drag. This depends upon the shape of the body, whether it is circular cylinder or sphere, or depending upon the shape of the body. Sometimes depending upon the case, increase in surface roughness may decrease the drag. So, here if plot taken from Munson et al., the fluid mechanics tested by Munson et al., here drag force coefficient for a sphere with respect to surface roughness is shown. Here the Reynolds number is on the x axis and the coefficient of drag is on the y axis. So, this is the case for a sphere. So, you can see that with respect to the Reynolds number and then the relative roughness of the sphere, the drag coefficient is changing, varying depending upon the roughness. So, if you consider, say for example, a golf ball, depending upon the Reynolds number, you can see that this is the pattern, and if it the epsilon by d, if epsilon is the roughness, then epsilon by d, whether d is the diameter of the sphere. So, you can show that, say with respect to Reynolds number, if the surface is very smooth, then initially the coefficient of drag is slightly increasing with respect to Reynolds number, and then after the critical range, when the flow becomes turbulent, we can show that there is a sudden decrease in the coefficient of drag, and then after a certain range there is again the coefficient of drag is increasing like this. So, for various parameters of epsilon by d, epsilon is the roughness and d is the diameter of the sphere, then you can show for various cases with respect to Reynolds number, the coefficient of drag is changing like this. So, epsilon by d is equal to 1.25 into 10 to the power minus 2 gives this curve, and then epsilon by d is equal to 5 into 10 to the power minus 3 this curve, and epsilon by d is equal to 1.5 into 10 to the power minus 3 like this, and this gives epsilon by d. Epsilon by d is smooth. The epsilon by d is almost 0, that means epsilon is very less. So, the surface is very smooth, then we can show this is the case. So, here you can see that other than the surface roughness, also with respect to the Reynolds number, say the coefficient of drag or the drag force is changing. So, now another important parameter as far as the drag force or the drag coefficient is the Froude number. Say for example, if we consider a ship, the coefficient of drag for surface ship is a function of Froude number, that means the ratio of free stream speed to a typical wave speed on the interface of two fluids, example the surface of ocean. Then we can show that depending upon the Froude number affects the coefficient of drag changes. So, whether this depends upon the say various other parameters of the say the wave effects, and then so we can show that Froude number also has got an effect as far as drag coefficient or drag force is concerned. And then wherever the composite body, that means the body is a complex body where say different shapes are included, some shape is, some part is spherical, some part is say plane, like that different shapes are included for the body, concerned body, that means composite body. The drag on such a body we can approximate it as sum of drag on its various parts. So, that way we can find out the drag force or the coefficient of drag with respect to composite body. So, so far with respect to our discussions, say we have seen the drag force or the coefficient of drag changes with respect to the shape of the body, with respect to the Reynolds number, with respect to the roughness of the surface roughness, and also the Froude number or the compressibility of the fluid. So, the drag force changes or the drag coefficient is changing. So, all these aspects are considered while we design various shapes for say for example for automobiles or for ships or for while we design aeroplane or aircraft or the space shuttle, etc. All kinds of design we can consider. So, these various parameters which affect the drag force and then which influences say the movement of the particular body through either through water or through air. So, we can, if we analyze, say if we consider say for example automobile industry, say whatever the design this automobile industry which has given in 1950s or 1960s, now in 1980s or 90s or in 2000, the shape of the car or shape of the bus or shape of the truck, you can see that there are some changes. So, the designers understood the effect of this drag force or the coefficient of drag, and then they gave such a shape that the drag force effect on the vehicle, say for example car, is reduced. So, if you consider say these changes are shown in this slide here, that means the aerodynamic drag on cars and then the various shapes given or various shapes adopted by the car industries, you can see here. Say in 1920s or 1930s, you can see the shape of the car was like this, and then 1940s and 50s when we understood that this coefficient of drag or the drag force can be reduced, then the shape of the car has been changed to this. Then you can see that the drag coefficient earlier for this shape it was about 0.8, and then for this shape of the car you can see that the coefficient of drag is about 0.55 or about approximately equal to 0.6. And again in 1950s or 60s or 70s, again various experiments were conducted, and then again the different shapes were designed as far as say the shape of the car itself is different shape. You can see the drag force is, or the coefficient of drag is reduced. So, you can see that starting from 0.8 say in 1920s, then in 2000 the drag force is, say as far as car is concerned, the aerodynamic drag on car is concerned now, the drag is about 0.35 or 0.4 range depending upon the shape of the car. So, this aspect of the shape or the orientation we can use in the automobile design, say for example cars, bus or truck or whichever say automobile is concerned. Similarly, also this aspect is considered while we design aeroplane or while we design the ships, depending upon the say various parameters. So, finally, here as far as drag is concerned, as we discussed the coefficient of drag. So, if we consider two dimensional objects, we can see here say for example, when the Reynolds number is about 10 to the power 4. So, if you consider a circular shape, say here you can see the coefficient of drag is about 1.17, and say rectangular shape or square shape, you can see that coefficient of drag is 2.05, and the same if you put in this orientation, you can see that coefficient of drag is reduced, so that is equal to about 1.55. And similar way, if you consider an arc like this, if you place in the convex side or concave side, you can see if you place the arc like this, then the coefficient of drag is 1.2, but if you place it in the other way, then the coefficient of drag is about 2.3. And then also if you put as a semi spherical or semi circular shape, you can see the coefficient of drag is 1.2. And then at triangular shape, you can show experimentally that the coefficient of drag, if you put it in this fashion, it will be only 1.55, and the same triangle shape, if you put in the other way, opposite way, you can see that coefficient of drag is increasing to 2. And similarly, the flat plate which we put in the normal to the floor, then you can see that coefficient of drag is about 2. So, similarly, if you consider three dimensional objects, so if you consider say for example, the Reynolds number is more than 10 to the power 4, the coefficient of drag for a cube or a prism is about CD is equal to 1.05, and prism is concerned, this is for cube 1.05, prism is concerned CD coefficient of drag is 2.05, and then you can see that a hemispherical so coefficient of drag is 1.42, and it ranges from 0.38 to 1.17, which way you place. If you place this way or this way, the coefficient of drag is here, it is much lower 0.38, and here it is much higher 1.17 for the Reynolds number more than 10 to the power 4. And then say very similar way, if you keep the body say a hemisphere like this, then you can see that it is 0.42, and then if it is streamlined body like this in 3 dimensions, you can show that even when the Reynolds number is about 10 to the power 5, the coefficient of drag is much lower, it is about 0.04. So, like this, say depending upon the shape, depending upon the orientation, and of course, depending upon the fluid flow Reynolds number, we can show that the drag force or the coefficient of drag changes considerably, and then we can utilize this concept or the reduction in coefficient of drag or the drag force, we can utilize the design of many engineering problems, say either car or aeroplane or ship or many other designs. We can utilize this coefficient of drag aspect. So, now we have seen the coefficient of drag, then the drag force, and then also various parameters related to that. Now, next topic is, which is very important, which we want to discuss here, is the lift force. So, we have seen the drag force, say whenever, especially for the flow over a flat plate or for an object in a fluid, whether it is moving or whether it is stationary, it is placed stationary. So depending upon the case, we will be having drag force and also we will be having lift force. So if you consider, say for example, an airfoil like this, you can see that if the free stream velocity is like this, then the drag force is in this direction and then we have the lift force. So the force exerted along the direction normal to the flow is known as the lift, as we discussed earlier. So this is the lift force and drag force which you consider like this. So some objects are designed to generate lift. Say for example, aeroplane design is concerned, we can see that we have to design the shape in such a way that we want to create lift, so that we can lift the aeroplane with respect to when the plane is moving. So that some designs like airfoil or aeroplane wings, we are designing in such a way that we want to generate lift, but some designs like say for example car or bus or truck, we are designing in such a way that we want to reduce the lift effect. Since if we consider say the design of a car, we want to reduce the lift, since if lift effect also comes into picture, then the movement of the car will be, when we accelerate, then you can see that there will be more say friction, more the lift effect also will be affecting the movement of the vehicle on the road. So depending upon the case, say for some designs like airfoil or the wing of a plane or the airplane, we are designing in such a way that we want to increase the lift, and some designs we want to decrease the lift. So now in the next lecture we will be discussing further on this various aspect on the lift force and the coefficient of lift, and then another important aspect, circulation, with respect to whenever the body is also moving, then what are the effects as far as lift is concerned. So this we will be discussing in the next lecture.